So let's take a look at section 1.4. The challenge for me in working through 1.4 is that it's a whole hodgepodge of topics from your Math 1150 class that are all just crammed into here. Now, if you want to, you can use the QR code here to follow along with the link, or if you're on D2L, you can open up the link via here. But we're going to work through a bunch of examples here. Let me take a quick look at the first couple here and go through a few things that happen a lot. Now, in particular, you're going to be asked to simplify expressions. So this one I could think of as x times x plus 7. And x plus 7 squared is really x plus 7 times x plus 7. And in that sense, I can say, all right, well, let's cancel out the common factor, which would leave you with this. So the first one is true. The second one's kind of interesting, and I get this a lot. What do you think? Are these two things the same?
Yeah.
Yes.
Gonna vote for yes? It's tempting, and I wish it were true, but I'll tell you what. Why don't we think of a number here? Think of your favorite number. What do you want to put in here? 4, 5, 7, 2? All right, so if you put in a 2, 2 squared is 4, plus 4 would be the square root of 8. And over here, if I put in a 2, I'd end up with 2 plus 2 is 4. Is the square root of 8 equal to 4? No. So these things are not equal. It's tempting. I know it looks like, oh, you should be able to take the square root like that. It just doesn't work, does it? Unfortunately, no. Let's move over to domain and range. Now, the domain of a function is a set of x values that you can put into that function. Now, I kind of think of it sometimes like a microwave. In microwave, you put in anything. And then you say, well, wait, no, you can't put in metal. Oh, and you can't put in certain plastics. So there are things you can't put into a microwave. In the same way, there's things you can't put into a function. There's things to avoid. So what are those things to avoid? So those things to avoid fall in a couple categories. The first thing to avoid is 0 in the denominator. What else do I want to avoid? Well, it has to deal with our square roots and our even-powered roots. Yes, thank you. You can't have a negative underneath a radical. No negative numbers. And I know that looks like a hashtag to you, but old school, that stands for numbers under an even radical. So 4th root, square root, 6th root, etc. So those are a couple of things to avoid. When we get around to logarithms, we'll also understand that you can't take the log of anything that's not positive, etc. But for now, these are the big two that you're going to have to be on the lookout for. So your domain is everything except places this happens. Now let's look at this first example here. The domain of this polynomial expression. Your domain starts out as negative infinity to infinity. Negative infinity to infinity, and then we're going to eliminate places that have these kind of errors. Well, is there anywhere that the denominator can be 0? No, because there is no denominator, right? Is there any place that you could have a negative underneath the square root? No, because there's no square roots here. So here's your domain. It's just negative infinity to infinity. There's no points that we have to throw out. So that's your default domain. But in this next example, we could run into a problem. What could go wrong with this second example? Yeah, the denominator could be 0. So we need to figure out, well, where does the denominator equal 0?
If 2 equals -2.
Yeah, so you can set this equal to 0. So 18 plus 16 equals 0 means 8t equals -16, or t equals -2. Now that's where the denominator equals 0, but I don't want that point in my domain. So how do I write that then? Domain.
Infinity to -2 and then
-2.
union -2 to infinity.
Yeah, nice, nice. So in case you didn't hear that, it was -infinity to -2 union -2 to infinity. Now, I'm using parentheses around both of these because I don't want to include either endpoint. All right, I'm not including the -2. What would I have to write here if I wanted to include the endpoint?
Bracket.
Brackets. Nice. And so let's kind of practice that over here with this example. So for instance, if you're looking at the domain of this function, it's all the x values that appear on this graph. So the x values start at -3 and go up to 1. But am I going to include the -3? Is -3 itself part of the domain? No. Why not?
It's an open circle.
Yeah, you got a hollow dot here. It means you're not including that endpoint at -3, so that gets a parenthesis. How about at 1?
Yes.
Yes, we're going to include that, so it gets a bracket. Close bracket. Yes, close bracket. Let's take a look at things on the y-axis, the y direction. So this is your domain. And then the y direction is going to be our range. So let me just come over here like this. And let's do similar. Now, your domain and range, they're always left to right, bottom to top, smaller to larger. So your domain is going to start down here at -4 and go up to 0. So -4 to 0. And what you got to figure out is, are we going to use brackets or parentheses? And if so, where?
Bracket at the 4, parentheses at 0.
Good. Bracket at the 4, because we've got a nice solid dot here at 4, and a parenthesis at the 0. So, like that. And that's going to be your range. Nice. Nice. So a lot of times there's a visual aspect to this in determining domain and range. I don't expect you to necessarily always know what a graph looks like, but if you do have the graph, it is helpful. If you were to follow along with the link on D2L, here's our first one. So it looks like this. Eventually this graph will grow and grow and grow outwards in either direction, and it'll pass through every value of x. There's no restrictions on this. So its domain is everything. For this one, well, it looks like everything is graphed, except there's one point that's missing. This graph doesn't exist at x equal -2. And let's do this one in the opposite direction. We'll start out with a graph and then see if we can't figure out what the range is and the domain is. Take a look at this graph. Where does it start?
-5.
-5. -5 to infinity. So, all right, -5 to infinity. That's going to be our domain. Domain. -5 to infinity. Should I use a parenthesis or bracket for
Bracket.
-5.
Bracket.
So I can take the square root of 0, that's fine, that's just 0, so we're okay there. But how about the range? How are we doing on the range? Where does that function eventually drift to? What do you think the range is on that one?
0 to infinity.
All right. I got to vote for 0 to infinity. Is 0 going to get a bracket or parenthesis?
A bracket.
So that point is actually a point on the graph. So the graph actually gets down to 0. It touches 0, so 0 is included. If I wanted to include that as part of the range, should I use a bracket or parenthesis?
Bracket.
Bracket. Thank you. Bracket. Let's take a look at this next one. Find the domain of this expression. Well, is it just negative infinity to infinity? Can I just say it's everything?
No.
What's my worry about this?
You gotta factor in the bracket.
Got to factor the denominator. What you're worried about is where the denominator is 0. So the domain of x squared plus 7 over x squared minus 3x minus 28. So we're worried about where x squared minus 3x minus 28 equals 0. So we want to figure out where that's true. And yes, I hope that the first thing you would do when you encounter a problem like this is to factor it. How's that one factor?
X
X
4,
minus
X
7.
minus 7.
Good. X minus 7, x plus 4. So Lucas, what does that mean our solutions are?
X equals 7 and x equals -4.
7 and -4. Now here's the tricky part. We don't want these as part of our domain. So, I mean, you could just say, all right, x is not equal to 7, x is not equal to -4. That's one way to write it, but WebAssign's going to want it written as an interval. So basically what we've got is kind of a number line. And it's not a bad idea to draw things visually for yourself. You have -4, 7. And then I want to figure out what each of these intervals are. So there's one to the left of -4. What would that one be?
Negative infinity, -4.
Negative infinity, -4. Amber, does -4 get a bracket or parenthesis?
Parenthesis.
Good. Parenthesis, thank you. Union, and then -4 to 7, parenthesis. Union, 7 to infinity. So that's your answer in interval notation. Basically, it's everything but those 2 points. All right, looking good, looking good. Unfortunately, there's a lot of stuff in here that requires factoring. And because I know that people aren't really necessarily very good with the factoring, I put some links in WebAssign. You do your prerequisite review to see review of factoring 3 and 4 term polynomials, more practice with that, difference in sum of squares. These are videos from the previous course, but they're going to spend more time factoring there than we have time for here. So if you need to go back and review some, please do. If you're just watching this online later, you can go to my YouTube playlist for Math 1150, find some values or find some videos there. It'll be section 8.6 and 8.7. All right, let's keep going. Example C. So this is going to be more of the factoring stuff that I was alluding to. X squared minus x minus 56 over x squared plus 9x plus 14. Now, as tempting as it may be, you can't cancel out the x squareds. You can't cancel 7 into the 14 into the 56. These terms are kind of glued together. So I can't cancel into that parenthesis. I can cancel out entire sets of parentheses, but I can't cancel into that. So the trick is to factor this thing first. Factor first. So Ryan J, help me out in the numerator, please. Can you figure out two numbers that multiply to negative 56 and add to negative 1?
-7 and +6.
You're close. 7 and 8.
7 and 8, +8, or -8.
Yeah, good, good. So what you're realizing is that the larger of these, if this is negative, the larger one has to have that sign. So it'd be a -8 and a +7. Cool. Hannah, how about the one below that? X squared plus 9x plus 14.
X plus 2 and x.
Nice. And for convenience, I'm going to write it as x plus 7 and x plus 2, but same thing either way. And now comes the fun part, right? Now you can take out your Zorro pen and go, Olay. Now let's cancel those out. Now you're canceling the whole thing. I'm not canceling into a parentheses, I'm just canceling the whole thing. So you're just left with x minus 8 over x plus 2. Can I cancel the 2 and the 8?
No.
No, can't. Sorry, can't. So, bummer there. Now, the unfortunate part is that these factoring problems tend to get a little bit harder. So let's take a look at the next one. And the next one's just going to be an unpleasant reminder of stuff that we did in Math 1150. So it's going to look like this. 4 minus x squared over x cubed minus 8. Now, a lot of people overlook a little something here. It's not x squared minus 4. It's 4 minus x squared. And that part messes with people a little bit. So here's what I'm going to do. I'm going to factor out a negative from that numerator term. And if I factor out a negative, that's going to change the sign on both of these terms. That should be a minus there. There we go. Minus 8. And now, because this is an addition, I can switch the order. Minus x squared minus 4. This is going to be more familiar to you than the other one. And the cancellation, the factorization is going to work a little bit nicer too. So let's start with the easy part. Now I'm going to leave the negative out front. There's nothing that's changing that.
It's the difference of squares.
Yeah, it's the difference of squares. So x minus 2 and x plus 2. The denominator is a little bit more complicated. Faja got the last one. What do you think we have to do for the next one?
Difference of cubes.
Difference of cubes. Thank you, Brandon. So difference of cubes. What do I cube to get each of the first terms? An x here
So
and a 2 here. And some people are using a little trick that I teach in my math 1150 class, which is so same sign, opposite sign, always positive. So when we're talking about the signs, that one's the same, this one's opposite, and the last one's always positive. But I'll put in the signs last. Right now I need to figure out the terms that I need for each of these. And this is part of section 8.7. If you need to go back and do some review, use the links that I have on my D2L website. So let's take these two terms and try and generate these three terms. The first one, I'll take x times itself. X times x, x squared. 2 times 2 gives me 4. But I need to do something else to get that last term. What else could I do? Yeah. Thanks, Oz. X times 2, which I'll write as 2x. Let's fill in the signs here. So, Kyrene. Same sign, opposite sign, always positive. What's that going to look like here for the signs?
Same sign.
Minus,
Positive, positive.
plus, and plus. So, okay. So these two are the same. These two are opposite. This one's always positive. Wow, a lot of work for not a whole lot of gain here, right, Ace? Is there anything I can do now? Is there any simplification I get?
Cancel the x minus 2.
Cancel the x minus 2.
X minus 2. It's all that cancels. So after all that work, we simplify down to minus x plus 2 over x squared plus 2x plus 4. You could, if you wanted to, distribute that term in the numerator. But, you know, doesn't matter to me if you do or don't. So either way, it's correct. Just be careful that you don't lose track of that negative. All right. How are we doing on that one? Okay. Unhappy reminder that, oh yeah, we did that difference of cube stuff. Yeah, sorry about that. The troubling news is that it doesn't get easier from here. We're going to skip the next one. We're going to go down to this one. And that's because there's a lot going on with that one. I'm just going to copy that on a separate sheet of paper here. So 4x plus 5 over 2x squared minus 3x minus 5 divided by 16x squared plus 16x minus 5 over x plus 1. Well, it's the divided by part that I want to draw your attention to first. What happens when we're dividing fractions?
You
change flip.
multiply by the reciprocal.
Yeah, thank you, ladies. Multiply by the reciprocal. So, and before we forget, 2x squared minus 3x minus 5 in the denominator times, it's going to put an x plus 1 in the numerator and a 16x squared plus 16x minus 5 in the denominator. Now, I will go through and show you the long way of factoring this thing. But let's be clever. Work smarter, not harder, right? If you take a look at what happened in the last one, you notice we got some cancellation. We got some cancellation in this one too. So I kind of expect some cancellation here. And the only way we're going to get some cancellation there is if I have a factor like this. That is, in other words, if I have, say, I don't know, 4x plus 5 as one of my factors. That's just a guess, but we can check it out. Now, if my guess is correct, and this is 4x plus 5, why don't you see if you can't figure out what the rest of this would be so that it multiplies out to 16x squared plus 16x minus 5. See if you can't just use that as a hint. And tell you what, maybe the same thing over here. In the denominator, I'll have an x plus 1 term, and maybe there's something else there. But you've got to check it. Make sure that you get it right. Make sure that it actually does factor like you're hoping and expecting to. So how do we work this? How do we rework this? Well, we know that when we multiply the first two terms together, what should I get when I multiply those first two terms together?
2x squared.
The 2x squared. So if I've got one of the x's, what's missing from here then? A 2x. All right, so let's put in a 2x there. And then let's see. The last terms are going to give me a minus 5. So if this is a 1, what does that term have to be?
-5.
Negative 5. Nice, nice. Let's do that same operation over here. So if I got a 4x here, what has to be the first term there?
4x.
4x, good. So a 4x. And then the last term has to end up multiplying to negative 5, so what does this have to be? Negative 1. Wow, that's a lot easier than doing it the hard way, the traditional way. So, hey.
That was easy.
Yes, nice. All right, this is a times. Let's put parentheses around those because they're treated as whole terms. We can cancel out the 4x plus 5. What else cancels?
X plus 1.
The x plus 1. So does that just leave me with, let's see, 2x minus 5 times 4x minus 1? Is that my answer?
No.
No.
You have to.
No. There's something wrong with that, right? There was a numerator here. That numerator didn't just disappear, but really when you're doing this, you're dividing. And if I divide x plus 1 by x plus 1,
1.
gives me a 1. So there needs to be a 1 as a placeholder in the numerator. If roles were reversed, if I had a 1 in the denominator, I don't need to see the 1 in the denominator. I do need to see the 1 in the numerator. Now, if you're looking at that going, yeah, but what if I need to factor this and I don't have a hint like there's a 4x plus 5 term in it? Well, they're not fun to factor. And here's where I would suggest something called the AC method. I'll put the copy of this in the notes. If you wanted to look back at it, you'll be there. But the AC method starts out by multiplying the outside terms. 16 times negative 5 gives you negative 80. And then you're going to look for two numbers that multiply to negative 80 and add to positive 16. Now that 16 is coming from the middle term here. Now, if you can't do that in your head, then you're with the majority of us. What you can do is write yourself a little table. Write all the factors of negative 80, so 1 and 80, 2 and 40, etc. And then realize that the larger of these has to be positive, meaning the smaller one's negative. So then I just went through and said, all right, well, negative 1 and 80, that's adds to 79. That's not it. Negative 2 and 40, nope. Negative 4 and 20, that's my winner. So we'll go with that one. Those are the two numbers that you need. Now with those two numbers, you're going to split this up. Negative 4 plus 20 is 16. But by having it as these two split up, because we had this perfect choice, this will now split up into two binomials. Factor out the GCF of this one, factor out the GCF of that one, and then this is a GCF which comes out here, and you're done. If you're worried that, well, wait a minute, what if I put in 20x minus 4x? That's still 16x. Sure. If you do it that way, then you'll end up with something like this. 4x is a GCF here, negative 1's a GCF here, and it still finishes factoring. I won't pretend that these are easy. They're not. They're a pain. But there are some tricks that we'll discuss later, maybe when we get around to polynomials in chapter 2 or 3. But for now, they're just a pain. There's not much I can do about it. Comments or thoughts on those? Actually, I should just say, is there something about this that maybe you want me to go over a little bit slower or repeat myself? Because I'll be happy to help out. Okay. Let's flip to the back side of our handout. Who knows their grammar well? What's the word redundant mean?
Just like
Yeah, repetitive, repeat yourself. So I always kind of got a smile out of the fact that this subject in a lot of books, or these types of problems in a lot of books, are called complex fractions. It kind of feels redundant. Fractions are complex enough. What do you mean a complex fraction? Well, a complex fraction is something that has a fraction within itself. So you have a fraction and then another fraction. And so we're going to do a couple examples of simplifying complex fractions. We'll start with example D. So for example D, this is actually familiar territory, even though you might not realize it. So let's see, example D. We've got x cubed over x plus 6 divided by x over x squared plus 12x plus 6. Now, why is this a familiar type of example? It's familiar because you've dealt with stuff like a over b divided by c over d. When you divide fractions, and you've already told me this, you just multiply by the reciprocal of the second fraction. We're going to do the exact same thing here. You just have to recognize and realize that this is your numerator fraction. It's one fraction. And this is your denominator fraction. So I'll write this as x cubed over x plus 6. That's my first fraction. That's my numerator. Times the reciprocal of this one, which is,
The bottom one is 36 instead of 6, like the last one.
thank you. So the reciprocal is going to be x squared plus 12x plus 36 over x. Can I cancel the 6 into this 6 or 6 into the 12?
after you factor it.
Ah, nice. Good answer. After you factor it. So let's factor it. I've got x cubed over x plus 6. Let's put that in a nice parenthesis here for ourselves. And then I'm going to have another parenthesis up here. Yeah, we'll do it in 2. You could do it in 1, but we'll do it in 2. The numerator factors as well. Carter, remember how the numerator factors? Or Ryan C. X and an X. Two things that multiply to 36 and add to 12.
6.
6.
Sixes, yeah. 6 and 6. If you're playing the game of craps, that'd be boxcars. So let's take a look here. 6, x plus 6, and x plus 6. Both of those cancel, so let's do that. Is there anything else I can get rid of while I'm here?
X.
I feel like that one X.
One of the x's, good. Get rid of one of the x's, so let's do that this way. Get rid of you, and I'm going to make you a 2. So that's going to leave behind x squared times x plus 6. Technically, it's over 1. You don't need to show that. You can just write x squared times x plus 6, or you can distribute it, x cubed plus 6x squared. I don't have any preference for one versus the other. It's fine. I'd rather not see the over 1. If you write it, I'm not going to take any points off. Johan.
Would you put that on whatever sign, x squared, 6 plus 6?
You can put it in like this. It should take it like this. If it didn't, let me know. Because they, unless they say distribute your answer, then that should be fine. Yeah, see, now that happens a lot. It's like, oh, I was going to ask the same thing. So I hope you guys don't feel shy about asking questions, because I can only read so much into your faces. There's a fine line between a deer in a headlight and abject boredom. And I don't know what I'm looking at all the time. So, as much as I try, I can't always read your faces. So if there's something that you're not sure of, please ask. Yes?
It's always confused me. So, like, which is the most simplified form? The factored out form or the distributed form?
Yeah, I guess if I had to pick one of these, I think I like this one better because it is factored. What you'll find when we start working with polynomials and trying to figure out where these are equal to 0, that it's actually better to have something like this factored. And I'll show you why. Here, let me just grab a little sheet of scrap paper here someplace. Eventually, you're going to want to know where this crosses the x-axis. That's going to mean knowing where y equals 0, which is what's true on the x-axis. When it's factored like this, then I can say, oh, all right, well, I know where one of the places is that this crosses the x-axis, that's -6. And the other one is where x squared equals 0, but that's at 0. So just by looking at it algebraically, you can tell where this crosses the x-axis. So it's not a bad idea to have them factored. I like it. I like it that way. But for this purposes of this problem, it's fine either way. Yeah, good question. Good question. All right. So that's an example of a complex fraction, but it's not our only example. And the rest of these examples are going to have to be done a little bit differently. So the next one I'll look at is going to look like this. X minus x over y minus y over x. So I'm going to introduce you to some more vocabulary, and that is, these are secondary fractions. So I want to find the LCD of the secondary fractions. And I'll put secondary in parentheses to indicate that that's the secondary fractions. So basically I'm looking for the lowest common denominator of these two fractions. Can anyone suggest what that might be?
Y x.
Yeah, y times x, x times y. There's our LCD. By the way, how come I'm not just inverting and multiplying like I did up here?
It's different because it has oh my god, it has a minus sign.
This isn't just one fraction over another fraction. It's this whole term, and this one has a fraction, this one doesn't. So you can't immediately do it like you do this one because you don't have one fraction in the numerator and one fraction in the denominator. You got 2 parts in the numerator and 2 parts in the denominator. So here's our trick. We're going to multiply by 1. That's our trick. The question is, what form of 1 are we going to choose? Now, multiplying by 1 is not really going to change much, but if we do it right, then it will make a nice difference. So how am I going to do this? Well, I've got this wonderful common denominator that I just came up with, x and y, and I'm going to multiply by 1 in some form. That form of 1 I'm going to choose, and be careful, I'm going to write the xy up here next to this, and the xy down here next to that. The form of 1 I'm going to choose is xy over xy. how does that simplify? If I simplify just this, if I said, all right, simplify xy over xy, what does it simplify to?
1.
1. Good. So it simplifies to 1. But in order to get the cancellation simplification that I want, I need to distribute that term to both of these terms. So that needs to multiply here, and this needs to multiply here and here. And here's what that's all going to look like. It's going to look like x times xy over 1 minus x over y times xy over 1. So if you distribute that, and look at it all together, you get something like this. I didn't write it immediately, but a lot of times it helps people to think of this as being, say, x over 1 and y over 1. That should be a times there. It shouldn't be a minus. It should be a times. Now, the nice thing is that after this step, I should be able to get rid of all my denominators. When we multiply fractions, you multiply numerators, you multiply denominators. Kyle, what happens when I multiply the numerators here, please? What do I get? X times x times y.
X squared.
Did you say Kyle?
Yeah,
Oh, sorry, x squared plus, x squared y.
good. X squared y. Good. And Johan, you're anxious to help. Is there any cancellation in here?
You cancel the 2 y's.
Yeah. If I cancel the 2 y's, what's left in the numerator then?
X.
Yeah, x squared. So minus x squared. And now let's simplify the denominator. Nick, what do I get when I multiply these terms together?
XY squared.
Xy squared minus
Minus y squared.
minus y squared. Good, because the x's cancel each other out. Oops. X's, so y squared. Now, you should look for more cancellation and more simplification, but you're not going to really find anything. You can factor out an x squared from the numerator and a y squared from the denominator, but it's not going to simplify into anything better. So we can leave it like that, or you can factor it out. Either way works for me. If there is some extra cancellation, I do expect you to do that, but if there's not, we're okay. All right. Let's see here. How are we looking with this this one? This is a tougher one. If there's something about it that you're unhappy about, I'll give you the phone number to my dean. You can complain to him. Oh, I'm kidding. No, if there's something that you're not really keen on, reach out. The whole thing. So what I'm hearing then is you want another one like that to practice? You got it. Let's choose one that, you know, at first glance might be a little bit confusing, and that's this one. 8 x to the negative second plus 8 y to the negative second over x to the negative first plus y to the negative first. Doesn't even look like a complex fraction at all, does it? No, it doesn't. So why is it a complex fraction?
Because you have to flip off.
It's split.
It's negative.
Yeah, you got those negative exponents. So what happens when you have a negative exponent?
You have to flip it.
Flip it.
Yeah, you can put it on the other side of the fraction. In this case, it would be a denominator. So 8 over x squared plus 8 over y squared, that's our numerator. What's the denominator looking like?
over
X
X.
over 1.
Almost.
1 over X plus 1 over Y. 1 over
X over
Thank you both. 1 over x plus 1 over y. And now you've got 4 terms, 4 secondary fractions. All of these in orange are your secondary fractions. So I need the LCD of those secondary fractions. LCD
X and 1.
of the secondary fractions. And it's a little bit more than just x and y.
Is it 8xy squared?
8's not going to be part of it because 8's not in the denominator.
Oh, shit. Oh, sorry.
Kaylin, any suggestions? What would be the LCD there?
I know.
All right,
So
no
it's
clue?
more than
X squared, Y squared?
Yes, well done. Thank you. X squared, y squared. So the LCD is x squared, y squared. You just need the highest power of each factor that you see. There's factors of x, there's factors of y, but the highest power is an x squared. Highest power of the y's is a y squared. So that's our LCD. So 8 over x squared plus 8 over y squared, and then 1 over x plus 1 over y. We're going to multiply each of those by this LCD. And to make it a little easier, let's think of that LCD as being something over 1. So each of these secondary fractions is going to get multiplied by the LCD. So how's it going to look? Well, it's going to be x squared, y squared over 1 times this one. X squared, y squared over 1 times this one. And we're essentially doing here the same thing that we did a moment ago. I just didn't take the time to do this step where we're distributing this to both terms. But that's the net effect, is that you're multiplying each of the terms in the numerator and each of the terms in the denominator by that LCD. When you're done with this step, you should end up with an expression that doesn't have any secondary fractions. You should be getting rid of all those. Now, if you're watching this later at home on YouTube or something like that, you can pause the video for a second and then work it yourself. And you can also fast forward until I remove this. But I'm going to walk around and see if you guys are doing okay on this one. Try and simplify that.
I'm afraid that's right.
Okay. Just trying to figure out more.
Squared minus times 8 over x squared. Then an extra 8. So
I, so I did 8 times, I did 8 times less than.
yeah, but there's no plus here. If there's a plus, then you distribute. But since there's no plus, it's just 8 x squared y squared.
Okay.
Okay.
This has to multiply. Numerous times. This multiplies. You got it written twice. You got it written once.
X, Y squared.
Oh, okay. Squared.
Okay, that's what I did, cause I got, cause you just, it's 2, and you just take out the 1, and then you just hit that. You take, yep, same answer.
Yep.
So it should be that times each of these.
Like that.
And then this times
Oh, we
both of
got it
those.
extra.
So I've got, yeah, because
I got the same top part, but I
Yeah, you see, you got it right.
I see what you're doing.
Well, no, it's supposed to be X squared. 2,000 X squared.
I have to like literally cross.
8y squared plus 8x squared over xy squared plus yx. You do x squared. And then figure out.
Everything else.
What's your name?
Faja,
Faja. Yo,
Johan?
this is your first math class?
No, I took intermediate.
Oh, same.
I have to take calculus, so this is like pre-req.
For what, what do you like for?
I'm a science major, so
Sounds like your house there.
I really don't know.
It's hard.
Yeah, oh yeah.
Yeah, no, keep that top left. Top left.
I'm sorry, what's your name? I'm so sorry.
Faja,
Faja.
you can call me Faj.
Faja.
Yeah.
I was thinking of Sasha, like, no, that's not it. I'm like, it starts with an F.
I got this. Sorry,
Okay.
excuse the
Yeah.
chicken, but that
Faja. Faja.
That's right.
you scared me. When did you start it?
These are numerators. So you should have x squared, y squared, or 8x squared, y squared, over x squared. So, for instance, this multiplies, gives me 8x squared, y squared, over x squared.
That's what I'm thinking about. We could sway over there. In the corner, or
Thank you.
So. What happens when you multiply the nine?
I got it. I'm sorry. Thank you.
you said you had it right?
Uh-huh.
So I
Sometimes what helps me is I rewrite it because if it's too messy, sometimes you can mess up yourself. Yeah, at first, I got it wrong at first, but then I really looked at it and I wrote that wrong. I ended up doing it. So I cancel out, yeah, that's right, cancel out attributes. Did you get Oh. You kind of learned how to like
Yeah.
It looks good. From what I can tell, yeah, you just
We're gonna
want
multiply
X and Y. And then cancel out the Y, right?
Yeah, it's got the
So-
Y, with the one Y.
The secondary factor.
So it's the one Y is the X squared and then the Y.
That's where, yeah, so you got this
Yeah,
one cancels out one X. Y squared,
Yeah, it looks good.
so there's X squared plus Y squared.
No, it's X and then Y squared.
Oh, yeah, X, Y squared plus.
Yeah, well, probably dividing the one by the X squared, so I know I cancel out the Y, but not.
Yeah.
Lucas. Okay, so the trick here, and I'll take a little extra time here to do this step here. We're multiplying each of these terms, each of these secondary fractions gets multiplied by this term right here. Now I wrote it as a fraction just so that we can line things up. You've got numerators and denominators. So let's see. This is going to be 8 times x squared y squared. 8x squared y squared. It's not 8x squared 8y squared because there's no plus between there. There's no distributing. So you're just changing the order in which they multiply. That's the numerator. What's in the denominator? Ryan, J, what would be in the denominator of this product?
Oh, X squared, oh, sorry.
X squared.
X squared. Awesome. Ryan, you're a ventriloquist. That's pretty cool. All right. Let's take a look at the numerator term here. Again, 8x squared y squared divided by y squared. And just leave it. We'll do the simplification next. Let's turn our attention to the denominator. When I multiply these two terms together, what's that going to give me? Well, I mean, I hope the numerator is pretty easy, right? Times by 1, that's going to be x squared y squared. How about the denominator? X. And then the same thing over here, x squared y squared, except this time the denominator is y. We want to simplify these terms. Now, because I multiply by the LCD, I should be able to cancel out all these denominators. It's just a matter of figuring out what's left. So for instance here, x squared cancels. What's that leave me with?
8y squared.
8y squared, good. Some other voices for the next one. If I cancel out the y squared, now what am I left with?
8x squared.
8x squared. Over here, only one of the x's cancels, so I'm left with x y squared plus
X squared y.
x squared y. So it's just a matter of kind of slowing it down, writing that LCD next to each of your terms, multiply, then cancel. Now, if you want to do the cancellation up here, that's fine, but a lot of you seem to be challenged with this problem, so I took the extra step of actually writing out that product. Now, you can factor out the 8 from the numerator. It leaves behind y squared plus x squared. And in the denominator, you can factor out an x and a y. So that would leave behind y plus x. But there's no simplification here. These two things are different. This doesn't factor. There's no cancellation. So as far as I'm concerned on a test, or as far as WebAssign would be concerned, either of these is a correct answer. Whew. All right, I don't think I'll be hitting this button for that problem. Not this time, no. All right, let's do one last one. I'm gonna make a comment on one of the ones in the homework. And let's see, that last one I wanna do looks like this. This is example E, part of example E. X over X minus 6 minus 2 over X plus 7. Now, in order to combine these fractions, what am I going to need first? Common denominator. So let's work on a common denominator. And I need a common denominator for adding and subtracting, not for multiplying and dividing. So let's see, our LCD.
It's X minus 6, X plus 7.
Yes. You have to regard these things as whole terms. So your LCD is really going to be the product of both of those. X minus 6 to the first power, which I'm not going to write. X plus 7, again, to the first power. Now we've got to build up each of these so that they have that common denominator. So to do that, I'm going to multiply this first fraction by some form of 1. What am I missing here that I have as part of my LCD?
X plus 7.
X plus 7. So I'll multiply by X plus 7 over X plus 7. And likewise, over here,
X minus 6.
yep, X minus 6 over X minus 6. Now, let's multiply numerators and denominators. In the numerator here, I get x squared plus 7x over x plus 7, x minus 6. If I distribute the 2 in the numerator here, I get 2x minus 12 over x plus 7, x minus 6.
So we don't have to multiply the bottom, we just put them together?
You could FOIL this out if you wanted to. You'd end up with x squared plus x minus 42, but I don't see the point.
Okay.
And I'll circle back to that when we're all done with our problem here. But yeah, I would leave it factored, to be honest. Now, these have the same denominator, so I can subtract their numerators. So I'm just going to write the denominator once. And I can subtract the numerators. But in writing it like this, I've made a mistake. What's wrong with this?
You distribute those subtractions.
Oh, distribute the negative, the minus.
Yeah. So it's not really written, but it's kind of understood that there's a parenthesis around that. And if you wanted to write it without parentheses, then you have to distribute, which means a positive 12 rather than a negative 12. Oops, there should be a minus 6 there. X squared plus 5x plus 12 over x plus 7 times x minus 6. Now, Samira, you asked, should we multiply? My answer would be no. Because if this factors and it was going to cancel with the denominator, by multiplying it, then you'd have to factor it again and then look for cancellation with the numerator. So here, is there any factorization in the numerator? Is there two numbers that multiply to 12 and add to 5?
3 and
There's not. There's not. It's prime. So that's it. But if there was some factorization, I could factor it and I could immediately see if there was cancellation. And if there was, I'd do it. But it's harder to see that if you've already multiplied it back together. So rather than redo it and then undo it, I'm just gonna leave it factored here. So this is good. I'm fine with that. Last comment, if you were to do something like this problem here, which is also part of example E, the lowest common denominator is just gonna be 2x minus 3 to the second power. So this already has the LCD, which is your 2x minus 3 squared. So in order to get the LCD here, I would just multiply by 2x minus 3 over 2x minus 3. Should end up with 10x minus 15 over this one squared minus 3 over this one squared. And then you can combine like terms and finish it up. Well, you should be good from there.
Would you do that, you would do that on both sides, right? And 2x minus 3?
You don't have to do that on this one because this already has the LCD. So we'll just leave that one alone. It's this one that you need to play with a little bit. So, all right. These are good calculus problems. There are a forerunner there. I didn't get a chance to cover them. Maybe I'll put them as extra credit on the exam, but that'll do it. That'll do it.